Hello, everybody. Oh. Okay, hi everybody. Can you hear me? Some yeses. Good. Sorry, I've had a bit of an exciting last 10 minutes. The internet died. Internet dies, it's kind of like end of the world. But we fixed all that. So that's good. So internet's alive. It should stay alive. Are there any questions before I get started? I'm still setting up a bit, so maybe put in a question or two in the chat if you have any. And then we'll get started. We've got an exciting evening ahead of us. All right, let me do this a bit. Okay, I don't see questions, so let's get with it. So welcome to week 8. We're week 8, and it's running fast. So actually, just so you know, so next week is what's called the term break. So there are no lectures or practicals, but I'll still be having the consultation hour. And the week after is a normal week. Then there are 4 weeks after term break. But in that week, there's what's called here in Australia the Queen's birthday. So that's a public holiday. So there's no lecture here. But I'll have more consultation hours. So basically, we have this lecture now and 3 more lectures afterwards, one of which has the 3rd quiz. And you should have marked quiz 2 at some point soon, similarly with the homework. Importantly, with homework 1, assignment 2 is out, and just reading the assignment will probably take you a bit of time. It's quite extensive, so I suggest just starting on it sooner rather than later, even though it's due in quite a while. And this is the second and last assignment, right? So the 3rd piece of assessment, the project, I'll put out a description of what's on the project later this week. So you'll kind of know what the project is about. Any questions about that? No? Okay. So let me quickly just review where we stopped. I'll do so on the notepad. And then we'll get on with today's content, which deals with spectral properties, and it's actually very exciting. So, 1 sec. Back to this. This is week 8. Okay. All right. So So just a quick review of kind of maybe there was a chat in them somehow. So there's a question, you'll use Julia in the final project? Yeah, you pretty much, yes. I mean, if somebody really has a case against Julia and you want to use a different programming language, go for it. But Julia is the programming language of this course. So yeah, the final project certainly has quite a lot of computational aspects to it. It's about presenting and doing expositions of a subset of these things, of the use cases. Okay, so let me just quickly let's see where we were previously. So, you know, a good part of the course dealt with so far with AX equals B, the system of equations AX equals B. Although in other cases we just treated A as a linear transformation, right? You can treat a matrix as a linear transformation, or you can treat it as something specifying a system of equations. There are obviously other uses for matrices as well. And we dealt with a situation where B was not in the column space of A, was not in the range of A, and then there's no solution, right? So, you know, cases with no solution. So then what we did is we sought an approximate solution, and the approximate solution was X hat A dagger times B, or A dagger is A transposed A inverse times A transpose times B. So that's the Moore-Ponroe pseudo-inverse at A dagger, okay, that dagger like that. Okay, the assumption for the existence of this inverse was the fact that the columns of A are linearly independent. So A is skinny full rank, okay? We'll deal with cases where that does not hold later on. Not this week, but it'll be towards the end of the course, where we speak about SVD and other things. SVD, so we're still not in SVD, singular value decomposition, still not there. Okay, so there was this. There's also the projection matrix associated with the story, and that's just A times A dagger, and that's of course A times A transposed A inverse A transposed, okay? And we saw the projection matrix is symmetric, and the projection matrix times itself is still the projection matrix, because the idea of the projection matrix is you can, let me try and draw it like this. So you've got, say, let's say we're living in R3, and now I'll kind of draw a plane that is spanned by the two columns of A, say. Okay, so let's say A here, the plane is spanned by the two columns of A, and the story is that we have some matrix, some vector B here. Okay, and what we want to do is we want to project B onto this plane, and that will be P times B. So is a projection matrix square? Is a projection matrix a square matrix? Is a projection matrix square? Yeah, okay. It's said somebody believes so, yeah. I mean, it's, first of all, it's symmetric, so you don't call a matrix symmetric if it's not square, but also if you look at the dimensions, it's square. But also if you look at what it does, it takes these vectors here, the vector B is in R3, so in this example, say, you know, this is 3 by 1, and this is 3 by 2. So this is 2 by 1, right? That's kind of if you draw this in this story. And then P is a 3 by 3 matrix, which puts you from here onto there. It projects onto that plane. Okay, and some related stories to that we also saw, and you on this, of course, you spend quite a lot of time. That or a lot of time. I won't say a lot of time, but you spend some time. A can be decomposed into, for example, the QR decomposition, where Q is a matrix with orthonormal columns. And R is an upper triangular matrix. And there are all these things where you can stick the QR decomposition either into the projection matrix or into the pseudo-inverse and get kind of nicer formulas. And that's actually used computationally a lot. But we didn't do a whole lot with it further. Hold on one second. Dog is outside chewing branches. There's no tomorrow. I'm glad he's enjoying. Okay, so that was this story. Now then you had a quiz, and after the quiz we dealt with this the story of data where you have say points here, and you're fitting a line through these points, and each point is of the form, say, xi, yi. Okay, so that's an xi coordinate and that's a yi coordinate. Okay. And in that case, we actually saw how to convert this line fitting problem into a least squares problem by taking the matrix A to be a matrix of all ones and of the coordinates x1, x2 up to xn. And then our beta hat, so beta is the slope of the line. So the line you could think of, you can say, this is like, you can call this, you're fitting a function, and that function is f of x is beta hat times transpose times 1 and x, for example. Okay. So, or just you can write that as beta hat 0 times 1 plus beta hat 1 times 1 times x. Okay. So this is an intercept and this is a slope. So beta hat is nothing but a dagger y, okay? So where a dagger you'd get just like before. And one of the homework assignments you have deals with, you've seen this kind of fitting before with kind of all these formulas with summations and such. One of the homework assignments, or the first one actually, deals with this situation. But this curve fitting goes a long way. And when we have time, that'll probably be after quiz 3, I'll show you how to do classification with this and further things. But all I'm saying is that fitting, least squares data fitting is in a sense a special case of trying to solve this overdetermined system of equations. Okay, so that's where we were. Are there any questions about that? Okay. So what I'm going to do now is move on to the next story, which is quite fundamentally different, and there'll be relationships, but it's in a sense you could call it the kind of the second part of linear algebra. Okay, and it has to do with with spectral properties. So the word spectral, spectrum, kind of frequencies. This is kind of big words. But basically, that's a synonym when you speak about linear algebra with eigenvalues and eigenvectors. Now, I believe that some of you have seen eigenvalues and eigenvectors before, and probably a small, if somebody hasn't, would you just put a no, a little n, just so I kind of see? But I believe that some of you might have seen it long, long ago, and of course, you know, the treatment could have been different. Has anybody has anybody never heard of eigenvalues or eigenvectors? Okay, yeah, so that's what I was expecting. So one of the answers was mostly just the mechanics of finding. Okay, and we won't deal a whole lot with that. Of course, we'll do it minimally, but we're hopefully in the next 2.5 hours, we'll be able to go all the way down to something extremely powerful, which is in a sense the gateway to PCA, to principal component analysis. But there's a whole lot happening with this kind of spectral view of matrices. So first of all, we're dealing with square matrices. Okay, we're dealing with square matrices when we're doing this. Okay, so the matrix is square. You can't speak about eigenvalues of non-square matrices. Okay, and this is a definition. This is a definition. So you take some matrix A, and you take X, which is a vector, but you can't be the zero vector. You're not allowed to speak about the zero vector. And you'll call this an eigenvector with a corresponding eigenvalue lambda, okay, with corresponding scalar eigenvalue lambda, if the matrix operating on the vector is like the scalar operating on the vector. Okay, so that's what an eigenvector eigenvalue pair is. So you have the matrix A. You know, the matrix A can operate, think of it as a linear operator, and that's in the 3 blue, 1 brown video that I also sent a Blackboard message today too that I'm suggesting to watch. But the matrix A, you know, it operates on a whole bunch of vectors, but on some specific vectors, the big operation of applying the linear transformation A on X is just going to be stretching X by lambda. Or maybe lambda is negative, or maybe lambda can actually be a complex number. We'll get to that too. Okay. So if that holds, then X is an eigenvector and lambda is an eigenvalue. Now, we're not allowed to speak about the zero. I'm not even going to say it. I'm not going to say zero eigenvector. We're not going to allow to speak about eigenvectors when X is zero. So eigenvectors cannot be zero because zero always trivially holds here, right? So zero is too boring for us to consider, right? However, the eigenvalues, it can be zero. There's no restriction that the eigenvalues are zero or not zero. Zero eigenvalue actually means that A is singular, but we'll get to that. Okay. So that's what this thing is. That's what this thing is. Questions about this so far? I mean, that's so far just a definition. And we'll actually see that the eigenvalues tell us a whole bunch about how the square matrix behaves, and they also have a lot of uses. They have uses in dynamical systems, and they have uses in principal component analysis, and they have uses in factoring the matrices and many other things. Okay, so the first thing I want to do is just, well, first of all, just to get this running, I might need to restart it in one way or another. But this is just a matrix, 1, 2, 3, 4. And I'm just going to use the Eigenvals function, linear algebra, to give me the 2 eigenvalues for this matrix. So we haven't set it yet. Okay, let me just restart it. But a 2 by 2 matrix, this is good. A 2 by 2 matrix has a 2 eigenvalues. And a 3 by 3 matrix has 3 eigenvalues. And a n by n matrix has n eigenvalues. So when we have n eigenvalues, maybe they're distinct, maybe not, but there's not more than n eigenvalues. So you can treat the spectrum of the matrix as the collection of eigenvalues that the matrix has. Okay, let's give this guy another go. Okay, so the Julia function Eigenvals takes in a matrix A and returns a vector with elements being the eigenvalues associated with that. So what it does is it finds all of the lambdas for which such a thing exists. Okay, you'll see this in a second if this thing works. I'm not sure why it doesn't. Let's give it a sec. Okay. And in the meanwhile, I'll show this. The Eigenvex function returns a matrix whose columns are the eigenvectors. And when you take a matrix A and you apply eigenvals to it, then this eigenvalue lambda 1 will correspond to the first column of EV. And this eigenvalue lambda 2 will correspond to the second column of EV. Okay. Here I'll run it again. So you see, if I just do eigenvals, I'd get well, I actually get a 2-element array. But now lambda 1 is this first eigenvalue, and lambda 2 is the second eigenvalue. And if I run this guy, so let me do this in several steps. So here what we have is a matrix, but the eigenvectors are not a matrix. They're just returned in a matrix form when you use this specific programming language, Julia. And this actually inherits from MATLAB. It's the same in MATLAB, and it uses LAPACK, etc. Okay, so you get here a collection of this first column is an eigenvector, and this is an eigenvector. Okay. So you see the first eigenvector V1, I'll call it EV comma 1, EV colon 1, so that's the first column, and V2 is EV colon 2. Okay, so I'm just assigning names to these 2 eigenvectors. And then if I'd want to do, I'll just do the same thing that there. Look, if I do A times V1, I'm applying the matrix A on V1. This is where the matrix A took the vector V1. And instead, let's apply lambda 1 on V1. And it does the same thing, you see. V1 applied to by the matrix A is just V1 stretched by lambda. And similarly, I can do with V2. Okay. So what this thing here does is it just shows you that A times V1 minus lambda 1 V1, the norm of that should be almost 0, there's just numerical error, and similarly here. Okay, so these are effective zeros, right? So it just shows that what I'm highlighting, the left-hand side equals the right-hand side, and similar for the second one. Okay. Now, eigenvectors are not unique. Okay, so just to see that they're not unique, just take this equation. I'm talking eigenvectors. The vectors are not unique. So take this equation, okay, and multiply it by 3. Multiply the equation by the scalar 3. So I have here 3x. What I've highlighted is 3x. And I have here 3x. So is 3x also an eigenvector? Is 3x also an eigenvector? According to definition, yes, yeah, it is. Because I've, an eigenvector, we just care about the direction, and direction, can also be the negative. I can also multiply by -3, etc. So it's not like you got to be careful. It's not the eigenvectors. It's there is an eigenvector corresponding to every eigenvalue. But as we'll see shortly, and that comes from the fundamental theorem of algebra, eigenvalues are unique. Okay, you actually only have n as subset. So this is just a demonstration that eigenvectors are not unique. So here I have another eigenvector. I'm scaling by 2.6. So A applied on this other one is still lambda 1. Okay. Now, just so you know, there's also just an eigenfunction, and it kind of returns the whole eigen system. Okay. Now there's a question. So is it a column space or a subspace? No, it's not a column space, yeah, but every collection of eigenvectors associated with an eigenvalue is a subspace, okay? And it's actually a null space. You'll see that in a second, okay? In the clean situation, every eigenvector points in a different direction. In some situations, which are not as nice, we actually have that eigenvectors point in the same direction. Okay, so now let's deal with this thing, which is, well, how do we find eigenvectors? And you probably have seen this. Okay, you probably have seen this, but now let's do it once again, and that's kind of the key equation in a sense, and we'll see the characteristic polynomial. So I'll go back to the iPad. Okay. Okay. So our key thing was that AX was lambda x, right? And x is, we remember, is a vector not equal to 0. Okay. So and we want to ask, hey, for which lambdas does there exist such an eigenvector x such that AX equals lambda x? And those lambdas will be the eigenvalues of the matrix. Okay. So eigen, kind of in a form of German, I believe it means self. It's kind of the self. It's the numbers, the self values, and the safe vectors of the matrix. Okay, because it's the self of these directions. The vectors are the directions where, when the matrix operates on that direction, the vector just goes in the same direction, doesn't turn at all. Okay. All right. So what you can do is you can, of course, do, you can do a x minus lambda x equals 0. Okay. This 0 here is a vector. Okay. This 0 is there. And, you can also stick an I here. Why not? Okay. Because you can always stick an identity matrix to multiply a vector. And when you do that, then you can get A minus lambda I times the vector x equals 0. So lambda is an eigenvalue if and only if this holds, meaning that there exists some x, and that's if and only if this holds, and that's if and only if this holds. So, all of these are the same equation, okay? Now, look, we created this new matrix, and it actually doesn't really have a name in linear algebra. Its inverse sometimes has a name, and it's called the resolvent. But this matrix in its own right doesn't really have a name. But let's call this matrix B. So we now have this system of equations bx equals 0. Is b square? The square matrix, yeah. Everything's square today. We're now done with kind of non-square things. We're pretty much mostly square. Okay, so we've moved from the world of generally non-square things to square things, and there's reasons for that. You'll see. By the way, don't worry. We'll later on in the course we'll take the non-square matrices A, and remember we can always take a non-square matrix A and then do A transpose A, and this guy is square, the Gram matrix. Okay, so that will play a role in SVD, but we're not there yet. Okay, so B is a square matrix. Okay, so if I was to tell you that the columns of B are linearly independent, okay, and that's just like telling you that B is invertible, or just like telling you that B is non-singular, then what would be the only X that would satisfy this if the columns of B are linearly independent? 0, right? 0, right? Only the 0 vector, but X is not allowed to be 0. So hence here, what we want is we want this B guy to be singular. Okay. We want the B to be singular. Okay. B being singular implies that there are other X's here that are not 0 that satisfy this equation. Those X's are exactly the null space of the matrix B. Okay, so if B is singular, then there's a non-zero null space to the matrix B, and that means that you can actually find an X, and that means that there's a lambda inside. So this brings the criterion, the determinant of, let me now just write, well, I can write the B here one more time, feeling all color-coded for just a sec. Okay, the determinant of B needs to be, well, color-coded until we're not. The determinant of B needs to be 0, or the determinant of A minus lambda I needs to be 0. So you see, we've constructed a matrix and we've asked for it, and this is, the B is not one matrix, by the way. B is, B is like, it depends on lambda, okay? This is B depending on lambda, this is B depending on lambda, this is B depending on lambda, and this guy here, which is just B depending on lambda, is a family of matrices depending on lambda. We want the lambdas that make this thing 0, and that would mean that for those lambdas, any X in the null space of this B is going to be an eigenvector, and those lambdas will be eigenvalues. Okay. So it's kind of funny if you kind of think of it, because singular matrices are they're odd. If you take random numbers, you're not going to get singular matrices. But here, kind of by design, you're making this specific matrix singular. Okay. Now let me just continue on the writing pad with the example that's also in the Jupyter notebook. So just to see an example, and this is what many of you have probably done before. So if we take the matrix 1, 2, 3, 4. Then what we're looking for is the determinant of 1, 2, 3, 4 minus lambda, lambda, 0, 0. We want this to be 0. This 0 here is a number, yeah? The determinant is just a number, it's not a vector. It's not like this 0 here. Remember, 0 is the most overloaded guy in this course, okay? And that's the determinant of 1 minus lambda, 4 minus lambda, 2, 3 equals 0. Okay, so the diagonals, you subtract the lambda from the diagonals. Now, you can compute this, so that would be 1 minus lambda times 4 minus lambda minus 6, right? That's a product of these two guys. Okay, that's 0. And that gives us an equation for lambda. Okay, that gives us an equation for lambda. What kind of equation is this? What is this thing in general? It's a quadratic equation, right? Quadratic equation, and you can solve it in one of different ways. Maybe you're able to manipulate and factor, maybe not. In this case, there isn't a nice solution, but that would be like lambda squared minus 5 lambda minus 2 equals 0, and then you say lambda 1, 2 equals, let me just write the formula. So you see negative b plus square root of b squared minus 4ac, all divided by 2a. where, you know, and this is just a quadratic formula. So, right, so this is A, this is 1, and this is the B, and this is a C. Okay, and if you do this in this case, you get some numbers, and we'll see that in Jupyter in a second. Okay, of course, in other cases you might have been able to factor, and there are actually other ways to compute this by hand. This is not the way a computer would compute this. Now, importantly, this guy here, you can write it, let's call it P of lambda. It's a polynomial in lambda. And the degree of the polynomial, what's the degree of a quadratic equation? If we think of it as a polynomial, what's the degree of a quadratic equation? 2, okay? And if we had an n by n matrix, the determinant will be, well, the determinant of this guy will be an nth order polynomial, okay? So finding eigenvalues is like solving nth order polynomials associated with the determinant of this guy, okay? And that gives you the eigenvalues. Okay, now then once you've found the eigenvalues, well, you can then search for the eigenvectors. And I've already said the eigenvectors, let's say now I'll actually put the numbers that we get in Julia. So lambda 1 is approximately 5.37. These are ugly numbers. And lambda 2 is minus 0.37. Okay, so these are the two eigenvalues. By the way, they both happen to be real. Are the things that we get here always real valued? Oh, sometimes no, right? So sometimes what you're going to get is you're going to get that this thing here is negative, okay? Or in general, for a polynomial, you can get non-real solutions, right? So, and you know, the square root of -1, we denote that I, and then you do yada, 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 and you get complex numbers. And these complex numbers for real polynomials will always be complex conjugates. We'll get to that a bit more, but we're also not going to use a whole bunch. But the thing is that eigenvalues of a real matrix can actually be complex. We'll see an example for that. Okay. Now, once you have these, then, you know, you have then the, if you look at now A minus lambda 1I, this was like one specific B, and you'll ask what X is in its null space, okay? So any X in null space of A minus lambda 1I is an eigenvector associated with lambda 1, okay? And similarly, if you would have then stuck lambda 2 here, then, you know, it's in lambda 2. Okay, and that's how you get the eigenvectors. And we won't worry about that a whole lot, okay? So you don't get you don't get a single eigenvector, you get a collection of eigenvectors. Okay, because it's a null space. The nice cases are when this null space, this null space is one-dimensional. Okay, in one-dimensional. All right, but that doesn't have to be the case. All right, let me go back to the Julia, and that was kind of a mechanistic description on what to do with eigenvalues. But now we're going to get to the slightly more fun properties. Let's see if you could see this. Yes. Okay. So you see that's exactly what we did in the notebook. And in this case, you know, I'm actually calling A, B, and C. I'm just solving the quadratic equation purposefully by hand. Well, sort of by hand. Negative b plus the square root, negative b minus the square root, okay? And you get the two eigenvalues. So of course, if you do that, then, you know, the determinant, you've set those lambda 1 and lambda 2 such that the determinant of this b here and of this b here are each going to be 0. Okay, that was how we got the equation, okay? And you can use the null space function. Null space returns you a matrix whose columns are the null space of a matrix. So the null space of this B is going to be, for example, one eigenvalue, and the null space of the second B will be another eigenvalue. Now, if you would have done eigenvex, you would have used the built-in function, you would get in, sorry, did I say value? I mean vector. The null space would be one eigenvector. I do this a lot, eigenvector. okay, as opposed to eigen the value, which is a number. Value is number, vector is vector. Okay, and the eigenvex function happened to return us the same eigenvectors. But again, we could have had, if somebody else would have implemented this, they might have wanted to multiply this by this eigenvector, the minus 0.82 and the plus 0.56. They might have wanted to maybe multiply this by 70, just because they felt like it. By the way, in the implementation in Julia, what do you think is a property of the columns of the null space or of the eigenvex? I mean, what would you, if you were kind of going to create a numerical package that returns you vectors and you can choose a whole collection of vectors, which one would you choose? What's the norm? Normalized. Okay, so there are two answers that we got. Somebody said normalized, so indeed norm V1 is this, and norm V2 is also one. Okay, so indeed we get the normalized according to the L2 norm. There was a different answer that said orthogonal, but orthogonal, what you'll see is towards the end of this evening, or this afternoon if you're in China. So orthogonal is a nice property you're guaranteed to get if the matrix is symmetric, but in general, you're not lucky enough to have that. Okay, so mostly these two, the V1 times V2, the inner product is not going to be zero. They're not orthogonal. Okay. We would have loved for them to be, but they're not. Okay. So it happens that the linear transformation A does not have orthogonal eigenvectors, and there's, you know, sure, I mean, we can apply Gram-Schmidt on this, but then we lose the structure of the eigenvectors. Okay. So let's run through a whole bunch of examples and properties. Now, this can be maybe a bit boring, but I hope you can maybe enjoy it because it's kind of this basic equation. Basically, ax equals lambda x, that's a basic equation. You got to keep this in mind. And the second basic equation is the determinant of a minus lambda I equals 0. Okay, so a lot of examples and properties just fall out directly from that. Some require just minimally more work. And there was a question, would they be orthogonal? No, they won't. They won't. So unless we're very lucky, the eigenvectors are not orthogonal.
Sorry, Yoni, I was just asking, if the null space is two-dimensional, would they be orthogonal?
Oh, good question. So if the null space is two-dimensional, so no, the null space, you can get an orthogonal representation of that, yes. So that's a good question. So thank you for the question. So if you happen to have a null space that's two-dimensional, but for this, it's quite rare because the eigenvalue itself has to be repeated, although we didn't get to this. So the algebraic multiplicity of an eigenvalue, I'll just say this and we might not even teach this, but the algebraic multiplicity of an eigenvalue is the number of times the eigenvalue is repeated. Okay. The geometric multiplicity of the eigenvalue is the dimension of the null space associated with that eigenvalue. So for the null space to be two-dimensional, you have to have the eigenvalues at least repeated twice. Okay. But yeah, that can happen. But it's not the common case. Let's just call it that. And this is kind of related. So if we have a diagonal matrix 1, 2, 3, so this is just a diagonal matrix, okay? Well, eigenvalues of diagonal matrix, let's just do this in our head, okay? Let's do this thing, a minus lambda I in our head. So just, unfortunately, I can't easily draw on the screen, but do 1 minus lambda times 2 minus lambda times 3 minus lambda. You know what, let's do it. So what you get is a characteristic polynomial of lambda is 1 minus lambda times 2 minus lambda times 3 minus lambda. So the roots of this characteristic polynomial are just 1, 2, and 3. Important thing, and this is also relevant to your homework. So a polynomial you can present in coefficient form where you And I think that in the practical, I don't think, I know in practical last week you dealt a bit with polynomials, but you can represent in coefficient form where you'd kind of say, you know, like this is a third order polynomial. You can represent this as a0 plus a1t plus a2t squared plus a3, although you won't need the a3 in this case, times t cubed. Okay. So you can represent the polynomial like that, and to get the a's, you need to expand, or you can represent the polynomial like that, like this. Which representation do you like more, the left one or the right one? Which one gives you more information? Which representation gives you more information, this left one or the right one? Right, the left one is great because it's already solved for us, right? So the left one is already kind of factored for us. Okay, so of course the eigenvalues, and from this you see, so the eigenvalues of the diagonal matrix are of course just the elements of the diagonal. Okay, let's go to triangular matrices. Okay, so triangular matrices are easy. Okay, in the same way that you just read off the elements from the diagonal. Okay, now this property comes from the fact that the determinant of a triangular matrix is the product of the elements. Okay, so the determinant of this guy in general is going to be 1 times 4 times 9. Okay, so, or, you know, so the characteristic polynomial is, again, you don't care that you have stuff in lower diagonal. So triangular matrices are just as easy as diagonal matrices. And I don't think we ever proved this property of determinant, but determinants of triangular matrices are the product of the elements of the diagonal. Okay, now let's create this matrix, A. This is an outer product. And this matrix is an outer product. It's an outer product of the column vector 1, 2, 3. This guy's a column vector times the row vector. Well, it's an outer product between these two vectors, and you could treat it as a matrix product between a column and a row. Okay, so this is obviously a rank 1 matrix. Okay, so the eigenvalues in general of singular matrices, or a singular matrix has an eigenvalue 0. Okay. And in fact, the number of non-zero eigenvalues is exactly the rank. Okay, and that comes again. So these are 0. This is a 0. This is a 0. Now, by the way, the algorithms that Julia with LAPACK underneath, or anybody else, the algorithms used to find eigenvalues are not these type of finite algorithms like backward substitution or Gaussian elimination or Gram-Schmidt. These were kind of finite time algorithms, right? So Gram-Schmidt kind of had a start and a finish, right? Gaussian elimination has a start and a finish. Give it a big matrix, it'll take a while to start to finish, might take a lot of memory, but there's start and finish. Eigenvalue algorithms are iterative, so they actually never stop. You only get closer and closer to the solution until you reach machine precision. And there are many reasons for that. One deep reason is the fact that solving for eigenvalues is as hard as factoring polynomials, and there's even a proof in algebra that you cannot find a solution, an explicit solution in finite time or anything like that for a polynomial of order greater than 5. I forget if it's greater or equal or greater. Okay, so just keep in mind that the eigenvalues are kind of approximate. But anyway, the other algorithms were also approximate because we were dealing with floating points. So blah, 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 this is zeros. Okay, and you have, so the rank here is 1. Okay, and you could think about why that is if you think about the null space, and again, the fact that we're looking for the null space of this matrix. Okay. So that's it. Okay. Yeah, so the rank of this matrix is 1. Now, block triangulars. We haven't dealt much with block matrices. Well, I mean, you've dealt, I haven't. You've dealt in the quiz with block matrices, but you know, there was just one block matrix with QR factorization. But here we have a block matrix where you've put A1 here. You see A1 is this 2 by 2 matrix. And A3 here is this 3 by 3 matrix, okay? Sorry, and A2 is this matrix. Okay, let me write it so it's kind of nicer. Okay. And you've also put like an A3 there in the top right column. So this is, you'd call this matrix block diagonal. So in a field that I like, it's called control theory. So that's kind of it uses a lot of linear algebra. So there's a lot of block diagonal matrices. So often we do things in block diagonals. And the eigenvalues of the matrix say, okay, we can compute the eigenvalues. Here they are. Now look, I'm going to compute separately the eigenvalues of one of this top right block. A1, you see minus 0.37, 5.37. They are two of the guys here. And I'm going to compute the eigenvalues of the 3 by 3 lower block, A2, and there are these guys, minus 32 and something close to 0, this guy, and 103. So the point is that the eigenvalues of a block diagonal matrix are the product of the eigenvalues of the two blocks. Okay. And this actually has to do with the fact that the determinant of this block diagonal is the product of the determinant. So in a sense, the characteristic polynomial of this 5 by 5 matrix, the characteristic polynomial of this 5 by 5 matrix factors into a second order characteristic polynomial and a third order characteristic polynomial. Okay. We won't see the proof for that, but that's another property. Okay. Now, eigenvalues can be complex. Okay, I've hinted at that. Let's see it. So this is kind of the most standard example. That's the 90 degrees rotation matrix. Okay, how do I see it's 90 degrees? Look, it takes the component, this unit vector on the x-axis that you'd sometimes call I, and it puts it like that. And it takes the second column, it takes this component, and it puts it like that. So it rotates by 90 degrees. Now, think about it. If you're rotating a vector by 90 degrees, you can't expect that, you know, if the operation of if the style of this linear transformation is to rotate a vector by 90 degrees, you can't expect that there'll be any vector that you'll apply A to and that vector will just stretch out. I mean, come on, guys. This is rotating the vectors. Okay, and that's why the eigenvectors will also be complex. So just to see the characteristic polynomial, let's just do it in our head or in semi in our head. So look, the characteristic polynomial here is going to be minus lambda times minus lambda. I'll write it like that, okay? Plus 1. Minus minus 1, which is plus 1 equals 0. Okay, or that's the, let's call this the eigenvalue equation. Okay, or just, let me just change it now live. We'll do this lambda squared plus 1 equals 0. And this is like the equation which you show. It's a quadratic equation that starts 1 unit above the x-axis. There's no lambda that intersects the x-axis. There's no real solution, but you can have two imaginary solutions. What are the imaginary solutions to this equation? And of course, you can solve this using the quadratic formula as well. So the imaginary solutions, one is, if you want to write the equation differently, I'll put equals -1. So I is one of them. So let's see. I times I is -1 by definition. And what's another solution? -I. So if I do eigenvalue, that's what I get. I get the two complex numbers, you see, with 0 as a real component, -I and +I. Okay. And the eigenvectors happen to be these complex numbers as well. So you see, we're dealing with real matrices and with real data, but we're forced to actually step into the complex world if we want to stay within this framework where we say, hey, a matrix has eigenvalues. And that turns out to be mathematically very beneficial. So it's, of course, the thing I only mildly said, but didn't say fully, is since this thing is an nth degree polynomial, it has n roots. It has n roots, and these are the n eigenvalues. Again, these roots can be repeated or distinct. And if they're complex, they'll be complex conjugates. And indeed, these two numbers are complex conjugate. Okay, a complex conjugate just means if you have a negative here, you have a positive here. Okay. All right. And let's just do together just before the break, 2 minutes. So the eigenvalues of a projection matrix. Okay, so for this, let's go here to the iPad, and then let's speak about the eigenvalues of a projection matrix. I mean, one can speak about this for longer, but we'll think about it for 2 minutes. So remember, we jogged your memory as a projection matrix square. Well, projection matrix kind of belongs to a different unit that was before, but thinking about the eigenvalues of a projection matrix is kind of nice. So take the projection matrix. So you now have in general A, which is, you know, n by n. Okay, so the projection matrix is A transposed A inverse A transposed. Okay, that's projection matrix, and that's a n by n matrix. Okay, let's think of A as skinny, so m is less than or equal to n. Okay, A is like a skinny line. Okay, that's a projection matrix. So before we actually do some symbolic computation, let's again take, this is now the plane. We had this drawing earlier today, okay? And the projection matrix projects onto, here we have, what we have here, these are like the columns of A. That's the columns of A, okay? That's the columns of A. Okay. So which vector, which vector will not change its direction? So let's say now again we have that kind of vector here that doesn't like to play along with this subspace that we're going to project. And is this vector an eigenvector, this purple one? I mean, when we apply the projection matrix to it, when we do P on purple, is it going to point in the same direction? So you see, if I'm now taking, I'm taking the projection matrix. Let's do it blue. Make the matrix blue here. I'm doing P on this. What's the projection matrix going to do? It's gonna drop this guy here. It's going to put it here. So could this guy here, this purple guy, could it be an eigenvector? No, not getting any risk. No, it cannot, because it's going to change direction. But okay, and how about this guy here? Can this guy be an eigenvector? Yes. Okay. Yes. So the eigenvectors are actually, well, it's the columns of A are eigenvectors. Okay, and just to see this, look, I'm just going to write. So sorry, I'll just start the break in a minute or two delay. So if I take this projection matrix and I apply it here to A, okay, applying it to A is just like taking it on the columns of A. Okay, so this first column of A, second column of A, third column of A, up to the nth column of A. Okay, what I'm going to get is I'm going to get again A. Okay. Now you could see this also algebraically. I mean, if you put here let's just write it. So if I do A times A transposed A inverse times A transposed, this is a projection matrix. Apply this to A. This thing cancels with this thing. Beautiful, no? And that equals A. So what are the eigenvalues? And so this is like a combination of many equations together, where you have, for each column of A here, you've got a column of A. You can treat them like all together. So what are the eigenvalues associated with these vectors, with the columns of A? What are the eigenvalues associated with the columns of A? 1. Beautiful, beautiful. So you see, you're just, when you have a matrix P times something, if you have Px equals X, then you say, this is like having a 1, so X is an eigenvector with an eigenvalue. All right, so we see that lambda equals 1 for poles of A. Now, just one more thing. Is there another vector that you project on that you can apply a projection to, and you're actually going to be very disappointed? So let's go back to the geometric drawing. So let's be here a second. So there is some vector here in the space that we can apply a projection to, and we'll say, ah, come on, that's your projection. This is what you're doing. This is what we get, but that's what we can do. So, there's kind of zero information in that vector with regards to this subspace. So what is this vector? How do I draw this? This other vector that I project onto the space, and it actually puts me at 0. Where do I need to? It's a right angle one. Perfect. So you see there's a vector here. There are vectors here. And these vectors, if I project them, I end up exactly here, exactly at 0. Now, these vectors are not the 0 vector, but these are, it'll put me there. So let's look at those. Let's just look at those. So then I can say the projection matrix applied to, I'm going to put this, this orange vector. Okay, this orange one is this orange one. Okay, this orange one is this orange one. Should actually put us at 0, at the 0 vector. Well, the 0 vector, I can, instead of writing 0 vector, I can say the 0 number times the orange one. Okay. And this is my eigenvalue. Okay. Or I can just say the 0 vector. So these vectors here are exactly in the null space of the projection matrix. And they will have lambda equals 0 for null space of P. So that's just kind of a conceptual exercise connecting both projection matrices and eigenvalues and eigenvectors. All right. We'll see. Maybe we'll just play with this just after the break. So let's continue it in Brisbane at 6:05, and I'll be back. So that's 10 minutes from now. So you get the full 10-minute break. I'll be back in 5 minutes. So the initial connection was we just took another example of a projection matrix, okay? And then we said, okay, this is a projection matrix. What are its eigenvalues and eigenvectors? And this is a very general matrix because you can take any skinny full rank matrix and write this projection matrix. And it turns out that the eigenvalues are 1 and 0, and they're 0 corresponding to things in the null space of the projection matrix, and they're 1 corresponding to the columns of A. Okay, that's that. All right. We'll actually just play with this quickly just after the break. So see you in a few minutes. All right, I'm back, but we'll only start in 5 minutes. But if anybody has questions on anything. So just so you know, so here for assignment 2, you'll see a few references to the SWJ book. And most of the SWJ book is available, the draft, this is a draft book, is available online, free, but chapters 8 and 9 are not, simply because that was a decision of my co-author and mine not to put this online together with the publisher. So in Blackboard, if you go to learning resources, so this is just available for UQ students, obviously. You know, I'm not a big fan of Blackboard, but you've got Blackboard here. You can get the file from here. So you get the SWJ full draft, please not for circulation. So, and the reason that this is there is on chapter, I mean, this book contains more than what we need and does not contain a lot of material of the course. It's mostly not a book for the course, but there are a few references to chapter 8, linear regressions and extensions, and in the assignment. Okay, so you'll see that there's all the pseudo inverse and stuff like that, and you know, these types of things. So just so you know, so you have access to this book, so pseudo inverses you see, etc. Because the homework assignment, for example, deals with these slightly anachronistic formulas and things like that. So you'll see that here, right? So in chapter 8. Okay. Of course, I'm happy to get feedback on the book, but you guys are busy with a lot of other things in the semester, so don't go overboard. The homework, and you don't need to read the bits between. So this is kind of a full description of linear regression. You don't need to read the bits between the bits that are referred to in the homework assignment, but the homework assignment also refers to this example. So this example is a classic example called Anscombe's quartet. You might have seen it, and it's the fact that, you know, linear fit is not always the best. And the homework assignment relates to this guy. You know what this guy is. It's a projection matrix. And statisticians call it the hat matrix. God knows why. Okay? And maybe she doesn't, I'm not sure. And you need to derive this in a homework assignment to get the kind of this thing for a 2x2 example. But anyway, so the homework assignment is here. There's kind of a bit involved. You need to get all those things. Okay. All right, 605. So just to see an example of the projection matrix, so let's just take an example matrix. I just want to fix it so it'll be the same. Let's do a 5 by 2 matrix, okay? So here's a 5 by 2 matrix A, okay? I assume the rank of A here is 2, okay? Okay, A is rank 2. So, you know, it's going to be always the same matrix A. So the projection matrix is A times inf of A transposed. I think I can just do this. A transposed A times A transposed. Okay, that should be a 5 by 5 matrix. Okay. Right, so out of the 2 by 5 matrix, we created this 5 by 5 matrix. So the eigenvals of P are only going to be zeros and ones. So you see, we've got 2 ones for the 2 columns of A, and we've got here 3 zeros. Okay, and the corresponding eigenvectors are going to be either the columns of A or the null space of P. Okay, associated with that. Okay, more things before I continue. Very quiet class tonight. I mean, you're never disruptive. We have kind of the whole internet between us protecting me, but you're extremely quiet tonight. Or is it me? Maybe it's kind of that time in semester. Can you guys hear me, or have I been speaking to myself for the last 5 minutes? Yes. Okay, thank you. Tough time of semester, yes. I know, but this is kind of the, okay, so tough time semester, I know, hang in there. Just so you know, with this course, keep this in mind. So when you look at this course, you've got assignment, and you've got a quiz, and you know now roughly what the quizzes are like. It's not going to be a whole lot, and that's it. And then you have a project, which is kind of fun. So I hope you can, you know, focus on that, and then that's one less course for the final exam. And I have a message. We're dreading the onslaught of assignment 2 and quiz 3 together. Okay, well, you know, fight it. You could do it. I don't know what to say. No, I'm sure you'll enjoy. All right, many more properties of eigenvalues and eigenvectors. So if A has an eigenvalue lambda and corresponding eigenvector x, then what happens to A squared? So here, you know, you've got a new matrix A squared. So all you need to do, I'll just write it here quickly, is all the time for these properties, just remember AX equals lambda x, the defining property. So take this guy and multiply it by the left from A, okay? On both sides of the equation. So I'm going to do that. You'll get A squared equals, and that A just squeezes past the scalar like that, is lambda AX. Okay. But what is AX? AX is nothing but lambda x. So that is lambda squared x. So you see, lambda squared is an eigenvector, sorry, an eigenvalue associated with A squared. That's kind of nice, no? All right, and x is still the same eigenvector. Or again, you got to be careful, x or any multiple of it is the eigenvector associated with lambda. Okay, here's the numerical demonstration of that. Oh, let's actually do this because this gives us complex eigenvalues. So just, I actually picked the seed like this. So look, I picked the seed, I played with the seed until we got a matrix that had a nice spectrum. So you see these two? The complex conjugates. The third one is just a complex number or an imaginary number? Well, from Julia's perspective, it's a complex number because it's a complex type. Because Julia, once it kind of noticed that one eigenvalue is complex, it just made everything an array of complex. However, mathematically, it's a complex number whose imaginary part is 0, so it's a real number. Okay. Okay, and of course, you can't have. Could I have had 3 complex numbers here? Is there a 3 by 3 matrix that would have had 3 complex eigenvalues? A 3 by 3 matrix that would have had 3 complex eigenvalues. A 3 by 3 matrix that would have had 3 complex eigenvalues. No, right? Because you need 4 by 4, right? That's what's said there. Because if I get 2, these are complex conjugates. So the third one has to be real. Okay. All right. Now look, lambda 1 is the first element of the eigenvalue, is like this guy. And if I now do the eigenvalues of a squared, and let's look at lambda 1 squared. So this is this guy. You see, so when of course, how do you square a complex number? You need the arithmetic of complex numbers, which you don't really need to work with for our course. You'll manage without it. This is not something I'll throw at you at the quiz or anything like that. Okay, but you could think of the complex numbers a plus bi times c plus di and multiply the parts and all that. Okay, so that worked. Next claim. If A is non-singular and has an eigenvalue lambda corresponding to eigenvector x, then A inverse has eigenvalue lambda corresponding to that eigenvector. So this just means that the eigenvalues of the inverse are the inverse of the eigenvalues. That's kind of nice. Okay, so the eigenvectors stay the same. So just to see this one, let's do on the writing pad. It's just a bit easier to write it. So we have ax equals lambda x. Let's now take determinant of a not equal to 0. So a is non-singular, so a inverse exists. So let's just multiply this thing by a inverse. So a inverse a x equals lambda a inverse x. I pulled that lambda out already there. Okay, so what we get here is x equals lambda a inverse x. So what do I do now to find the eigenvalue associated with x for the matrix A inverse, our new matrix A inverse? What can I do? What can I do? And I want to find what's an eigenvalue of A inverse. I mean, I have this equation. Lambda is an eigenvalue of A. What's an eigenvalue of A inverse? So this is not, I want something, I don't want exactly this equation. Where do I want lambda to be? Lambda, you need to multiply what? You need to divide by this exactly. So I want to bring this over, right? So then I've got 1 on lambda x equals A inverse x. Okay, or if you prefer to write it, I'm just switching the order so it looks nice. And do this, okay? Now, I could divide by lambda because the matrix was non-singular. So this implies that all lambda i's are not equal to 0. Okay. So that's what happens to the eigenvalues of an inverse. All right, good. So that's another property. So you got all of these fun little properties. They all deal with the same thing. Let's continue just a bit more. Sorry, chat up. Okay, so and the next property, and this one I'll let you do this one just by yourself later. Oh, okay, you could look at inverse to the fourth and things like this. Okay, so these two properties are especially useful, well, they're super useful for 2x2 matrices. They're also useful for quizzes because they kind of allow you to extend the problems from 2x2 problems to 3x3 to 4x4, okay, and stuff like that. So the determinant of a matrix is a product of the eigenvalues, okay? So, and the trace is the sum of the eigenvalues. Okay, the trace, I should say, just to be clear, the trace of the matrix, sum of diagonals, is the sum of the eigenvalues. Okay, so let's see this. We've got a 5 by 5 matrix A. If I take the eigenvalues and I take their product, so I'm multiplying the eigenvalues by each other, I get this thing. Is this thing that I've highlighted, is this a real number or a complex number? This is from line 4. So it's real, yeah. The complex is just noise. So the fact is, I've multiplied complex numbers by each other and things canceled out. So the eigenvalues of A, just so you see them for this matrix, the eigenvalues of A, there were some complex elements in the spectrum. You see, there's these two complex conjugates. The second and the third are complex conjugates. Okay, and the determinant happens to be the same thing. Now, trace is the sum, so the same type of thing. So the sum of these guys is the trace. So if you think about it, for a 2 by 2 matrix, instead of computing the determinant, you can basically, instead of computing the characteristic polynomial of taking A minus lambda I and computing the characteristic polynomial, you can say, I'll sum up the two elements, and that'll be the product of the two eigenvalues. And it'll be the sum of the two eigenvalues, and then I'll compute the determinant, and that'll be the product. So I won't show the proofs for these, but they're multiple, but they come also from diagonalization. You try to write for yourself, try to show yourself this proof already later on tonight or tomorrow if you can. Just playing around with these things, and you can see how it works. The proof for the trace requires just a bit more, but we'll see it with diagonalization soon. Here's a very trivial claim, and you might expect this. Scaling the matrix, meaning multiplying by the scalar, just scales the eigenvalues, obviously. So just visualize in your head this the basic equation, ax equals lambda x, okay? The basic ax equals lambda x equation, multiply this by 3, so this multiplies by 3. So x is still an eigenvector, so you've actually scaled the eigenvalues by scaling the matrix A. That's different than scaling the vector x, okay? By the way, what's an eigenvalue of a scalar? What's the eigenvalue of the number 7? The number 7 is a 1 by 1 matrix. What's its eigenvalue? So we've got an answer 1, that the eigenvalue of 7 is 1. Let's try a second. So we've got A equals 7. Okay, that's this. We've got another answer 7, right? So we want A times x should be like lambda times x. So we want 7x is lambda x, yes. So lambda is 7, okay? Okay, good. All right, so, the scalar is just its eigenvalue. The thing is, when you get to a matrix, you suddenly, the 2 by 2 matrix already has 4 numbers, but how many eigenvalues does the 2 by 2 matrix have? Just 2 eigenvalues. So these 2 eigenvalues kind of tell you something about the matrix. The n by n matrix has n squared numbers, but it only has its spectrum, its collection of eigenvalues is only n, and that tells you a lot about the matrix. Okay, here's another claim. Adding a multiple of the identity to the matrix add to the eigenvalues and does not change the eigenvalues. So that's kind of nice. So you can take here's this matrix A. This is this rotation by 90 degrees matrix. Let's look at the eigenvalues. Remember the eigenvalues of A were complex. Negative I and positive I. Okay. The eigenvalues of 2i times A. So I'm now adding 2 to this guy. And try to prove this is another one. Whatever I'm not proving, I suggest to try to prove, and this is the type of thing that might be a small little quiz question or something like that. Okay, so you can scale the diagonal and still exactly what happens to the eigenvalues. That's kind of good. and you get the same eigenvectors. Now, this is also related to the important fact that, let me just put it here. Note, there is no special relationship between eigenvals of A, B, or A plus B. Okay, so if I know something about the eigenvalues of the matrix A and the eigenvalues of matrix B, once I take the product, I don't know anything really about the eigenvalues, and neither with the sum. Okay, now the next thing is the eigenvalues of A transpose, the same as eigenvalues of A. And you could see this because, you know, the determinant of A transpose doesn't do anything, right? The determinant doesn't care about transposition, and the eigenvalues just came. The characteristic polynomial does not change when we do a transpose. However, the eigenvalues are different. So, look, this is our matrix 1, 2, 3, 4. It has eigenvalues A, eigenvalues of A transpose, same one. But same ones, the eigenvex, or again, I don't want to say eigenvex, these are eigenvectors of A, and these are eigenvectors of A transposed, and they're completely different. And well, they're not fully completely different, they're somewhat similar in this case, but in general, you get different one. I mean, in this case, there's a relationship, but in general, you get a different one. Now there's a question, I don't get it, adding to the eigenvectors?
Hi, yeah, sorry, a few lines back up, I think it was the 2 claims up. I think you just had eigenvalues in there twice, and one of them should be eigenvectors.
Oh, I see. Which one might as well change it? So it's,
I think it's the next one up. This claim here. Yep.
Yeah, perfect. Thanks. Adding to,
Worries.
sorry, eigenvectors. Good stuff. Thanks a lot. Vectors. All right. Now, when you look at A transpose, so by the way, sometimes people, and this matters in some fields, you can call the eigenvectors of A transpose the left eigenvectors of the matrix A, right? Because it's like they're solidly on the left. Okay. Let's not deal with that more. Now, this claim is actually important to us, so maybe let's take a second just to prove it after we show the example. I mean, many of them are important, but this one will actually be important in SVD. So say we have 2 matrices A and B, and say that we can multiply AB and BA. Okay, I mean, what I mean multiply, first of all, we don't get like a syntax error. We don't get this error, syntax mismatch. I mean, that can happen if the matrices are square, but it can also happen if they're rectangular with the same dimensions. Okay, you'll see the example in a second. Now, this is really cool. The non-zero eigenvalues of AB are the same as the non-zero eigenvalues of BA. And this is going to be really important for singular value decomposition that will come later on. Okay, and then it's in general important. So let's just see the example here. Okay, so what I'm saying is you've got 2 matrices here that might even be of a completely different. So these guys, this AB and BA, they might be of a completely different nature. Okay, so one can be 4 by 4, one can be 6 by 6. Okay, there might be a completely different issue. Dash, come on. So I've got here. Since the class is so quiet, dog wants to say hello. Okay, that's it. Go now. Thank you. All right, so, you know, they can be of a completely different nature. All right, completely different nature, but the eigenvalues that are non-zero are going to be the same. Let's see this. Let's see this example. We're setting some random seed. What we do here is just rounding a number. That's all. Okay, that's just rounding a number. And we get some random matrix A, random matrix B. Okay, let's see. Just so you see it. A is this matrix, and B is this matrix. Okay, and because this is 4 by 6 and this is 6 by 4, you can do AB, you can do BA. You either get a 4 by 4 matrix or a 6 by 6 matrix. So, you know, you've got a 4 by 4 matrix as your product or a 6 by 6. And look at the eigenvalues of AB and look at the eigenvalues of BA. So you've got here minus 28 appears here, 3.5 appears here, 30.55 appears here, 550 appears here. Of course, the BA, the bigger size, you know, this is kind of like has some 0 eigenvalues. The rank of BA is only 4. Okay, but still it shares the same non-zero eigenvalues. Okay, so let's just see this. So you've got A, B, you've got BA. Okay, so let's take an eigenvalue of AB. That means that, or an eigen relationship of AB. So AB times X equals lambda X. Okay, now we're assuming here, of course, X is not equal to 0 because that's always in these relationships. I mean, these relationships are boring with X equal to 0. So eigenvectors are never equal to 0. But we're also assuming that lambda is not equal to 0. Okay, so lambda is a non-zero eigenvalue of AB. So we're looking at AB. So what we do now is let's multiply this on the left by B. I mean, we can do this multiplication. There's dimension matching there. Okay, they could have been square as well, by the way. Okay, but they're also rectangular. So multiply this on the left by B. So get this. Okay, multiply this on the left by B. So now let's just put the brackets here. Let's do this kind of trick. Let's put the brackets here. Let me write this a bit nicer. So what we've got is BA times the vector BX, this vector, equals lambda times the vector BX. So now the vector BX is not 0. Okay. Why is the vector BX not 0? Because lambda is not 0. So because lambda is not 0, we cannot have the vector BX was 0 because if the vector X would be 0, then am I correct? Let's see. The vector BX is not 0 because lambda is not 0. Yeah. If the vector, because lambda is not 0, it means that BX cannot be 0. And why is this? Sorry, I lost myself here for a sec. So lambda is not 0, so this thing, and X is not 0, so yeah, this thing cannot be 0. So that means that BX is hence BX is an eigenvector of BA with eigenvalue lambda. So we've just seen that lambda was inherited from AB to BA. And the same way works around backwards as well. Okay. So that's how AB and BA share the same non-zero spectral elements, even though these matrices can be in a completely different space, right? Or a completely different dimension, I should say. Now, just to say, this is going to be important, so keep this later because I might just get to it very quickly then and just say, oh, we've proved this before. When you look at the matrix A transpose A, what do we call this matrix? A transpose A? A transpose A, remember? It's symmetric, right? That's kind of an attribute of it. And it's a gram matrix. It's a gram matrix associated with A. A is like, you know, a matrix with data. Okay, A is a matrix with data, and that's the gram matrix associated with the matrix A. Okay, A is like skinny, so this is actually like that. This matrix looks like that. Okay, that's skinny and skinny. Okay, so it's so this is like a smaller matrix. Okay, that's a gram matrix. Now, this matrix is nice because it took a non-symmetric matrix, and like we said in the chat, it became symmetric. So we could speak about the eigenvalues of this guy. Now, you can also consider the matrix A transposed. This is not the same matrix. Okay, this is a different one. This one, just to see kind of what's happening here, this is like a skinny, say, times a fat. This is more like an outer product, okay? That's like a bigger matrix, okay? This is also a gram matrix, but it's a gram matrix of A transposed, okay? So it's also symmetric. It's a gram matrix of A transposed. Now, we've just shown that these two guys have the same non-zero eigenvalues, same lambda I not equal to 0, okay? It might be that for one of them, there are no eigenvalues 0, and for one of them, there is a lot. Like often for this, there'll be no 0 eigenvalues because it will be full rank. And this, you know, this is kind of too big, so you've got some 0 eigenvalues. But they have the same non-zero eigenvalues. Okay, so that's an application of this. All right, let's go to the next. Share here. Oh, okay.
Yoni.
Yes.
I'm guessing I know the answer, but I'm just curious, when you think about, as someone who lives and breathes this stuff, when you think about a data set and eigenvalues, do you have a personal interpretation of what eigenvalues mean for a data set?
Yeah, wonderful question. So, okay, so this is really the question of the course, so thanks for asking it. So, I mean, what do eigenvalues mean for a data set? So you see, eigenvalues, so far, we know how to use them for square matrices. I mean, they're always for square matrices. A data set will often not be a square matrix. However, when you look at a data set, often you'll compute the covariance matrix. And, you know, most of you probably heard of covariance here or there or elsewhere, and you'll see more of it in this course. I mean, that's kind of a very big interpretation. Okay, so when you look at the covariance matrix, then the eigenvalues are very, very important, and that's actually how we're finishing today. That's not the end of this unit, but that's the end of today. And then you can actually compress the data set. You can actually only get the elements with very high eigenvalues, and that's really what principal component analysis does. That's one way of looking at it. Now, the other way, and thanks for putting this on the chat, somebody else. So when you have a data set, and that's in the matrix A, the matrix A transposed A, the gram matrix, is actually symmetric. Its eigenvalues will be real. Their square root is going to be the singular values. And that tells you a whole lot. It tells you how much information is in each rank 1 approximation of the matrix. We're still not there, but that's where we're getting to. So, you know, for data, the big connection for the two aspects for eigenvalues, one is kind of spectral decomposition, which we'll get to today. One is singular value decomposition, we'll get to in 2-3 weeks. Okay. The other aspect has to do with dynamical systems, and that's where we're going now. Okay. All right. So we're going on to the next phase, and that's diagonalization and similarity. Now, I did take here the kind of the slightly more formalistic approach of just showing a bunch of properties, because I just thought that was still the best way, even though we're data scientists, because we actually want to control some of these aspects. So take a matrix A, and we're in square matrices, okay, this whole time, and A tilde. And you'll say that they're similar. You know what a similar triangle is, right? Similar triangles are triangles that are kind of, you know, ASA, whatever, they're kind of similar. And you say the matrices are similar if you have some non-singular matrix A, and this kind of relationships, which just like that looks a bit funny. You know, like M multiplied by A on the left-hand side is like M multiplied by A tilde on the right-hand side. Okay, but M is non-singular. So it's an invertible matrix. Okay. So just to see, this is equivalent to writing. Now, this might be slightly more appealing. This means that A is like M A tilde M inverse. Okay, so I've just multiplied by M inverse by the right-hand side. Or alternatively, I've multiplied here by M inverse from the left, and that's like saying A tilde is M inverse AN. Okay. So that's what you call similarity between matrices. Now here's the thing. If matrices are similar, then they actually have the same spectrum, the same eigenvalues. So it really means that they're kind of the same. Okay, they're just, in a sense, different representations of this operator in different bases. That's kind of what it means. So let's see this. Let's see this. Okay, now this, if some of you have studied this before, then you'd start to deal with this with diagonalization, and that's where we're going next. But I prefer to actually just start with similarity. Diagonalization is a special part of similarity. Okay. So what we're saying is that AN equals a M A tilde. Okay, that's a similarity. Okay. Or we could have just said A is M A tilde M inverse. Okay, so that M not 0. So let's look at eigenvalues of A. Okay, so to do that, of course, we look at the characteristic polynomial. So we look at the determinant of A minus lambda I. Okay. Now, if two matrices have the same characteristic polynomials, the characteristic polynomials have the same roots, they have the same eigenvalues. So a characteristic polynomial is really, that's the name, characteristic. It characterizes the matrix. Okay. So instead of A, let's plug in this guy. Let's plug in this representation here. Okay. So that equals the determinant of M A tilde M inverse minus lambda I. Now, I remember back in the days when we were speaking about determinants that we saw that the determinant of BC is determinant of B times determinant of C. This is when B and C are square matrices, okay? I mean, if you could still have that this guy is square, but this makes no sense, okay? Keep in mind, right? So we're speaking about square matrices, okay? So determinants factor like that. So that's what I would like to get here. But the problem is that I have here on this left-hand term, I've got m's, and here I don't have m's. So what can I do with I? How can I represent I in terms of m's? How can I represent I in terms of m's? So whenever m is non-singular. So give me a m times m inverse, right? So I is just going to be m times m inverse. So let's write the determinant of m a tilde m, sorry, I'm writing like a jerk, m inverse minus lambda m times m inverse. And now I can take this and I can just do some basic factorization, use a distributive law of matrices backwards. So I can factor these two m's out, and I can factor these two m tildes out. So let's do that. So that's the determinant of m times a tilde minus lambda I times m inverse. And determinant of product is product of determinants. If these things are square, that also holds for three matrices. So from the two, you can also go by induction to any number. So that's the determinant of m times the determinant of a tilde minus lambda I times the determinant of m inverse. The determinants are already numbers, right? So what's the determinant of an inverse of a matrix if the matrix is non-singular? Okay, so what happens with this guy and this guy? It's 1 over the determinant. Perfect. So, you know, I can just then cancel this and this. So I've gotten that that equals, oops, no Siri, not interested in no tips at the moment. No, okay. That's a determinant of A tilde minus lambda. Okay, so what we see is that the characteristic polynomial of A is like the characteristic polynomial of A tilde, and hence they have the same eigenvalues, okay? So similarity is really, similarity, you're keeping the same spectrum even though your matrix is now looking different, okay? So far this might look a bit obscure, but now we'll get to the number, the most primary, but not the only similarity transformation that's very common, and that's the one that has to do with diagonalization. Oh, you've lost the iPad, sorry. Let's just see the iPad for another sec, thank you. Right, so the characteristic polynomial of A is like the characteristic polynomial of A tilde, and hence they have the same eigenvalues. Okay, so let's get back and now see what we can do with this. And this is strong, this is extremely powerful. You know, so mathematicians, we say something is strong when we feel that the audience is kind of not convinced or you feel it's getting too technical. But believe me, this stuff is strong, really good stuff. It's as good as it gets. Similar matrices share the same eigenvalues. You've just seen that. Okay, so the most basic way to find such an M, and that's the most common way, and that's the way that's often taught at first, is to do something called the similarity transform. Well, is to do something called diagonalization. In general, when you're doing this, when I'm doing this, this is called a similarity transformation. Okay, this is in general a similarity transformation. Now, you know what matrix I'm going to use for M? I'm going to use the matrix that has the eigenvectors as the columns. Okay, so this guy here is, I'll annotate now on this. So this guy here is M. This is M. Okay. And this is also M. Now, if I do this, then this relationship AM equals M A tilde, and then this is A tilde on the right. This guy here is A tilde. So if I do this, then I have a similarity between A and this very nice matrix A tilde, which is a matrix of the diagonals of the eigenvalues. But let's see that this actually makes sense. So that's kind of the plan. But let's see that this thing actually works. Okay. So you know, we know that AVI equals lambda IVI when lambda is an eigenvalue and VI is a corresponding eigenvector. So you can just write this. You see, AVI is, you write all of these n equations together. You write A times V1 is, and now here you're multiplying lambda 1 times V1. So when you're multiplying by a diagonal matrix from the right, you're actually, this matrix here that I'm hovering on is a matrix with lambda 1 times V1, lambda 2 times V2, lambda n times Vn, etc. So that's exactly that. And that means that everything is good. So M is our matrix of the similarity transformation. However, there's a condition on M. What was the required condition on M? What did we ask M to have? So M has to be invertible, right? So for this to work, for A to be similar to the diagonal lambda, M has to be invertible. And this is a case if you have a collection of eigenvectors that spans all of Rn. That spans all of Rn. in some specific cases that won't happen, but they're not the common ones that we'll speak about. And for symmetric matrices, it'll always be okay. And for cases with distinct eigenvalues, it'll also always be okay. Okay? So, you know, you'll just, I'll show you. All right, so the plan is now to do A equals M times A times lambda tilde times M inverse. So let's look at it. So we've got a matrix A, okay? And M is now the matrix with eigenvectors in columns. Okay, that's what M is. You know, is the det M not zero? Thank God. Oh, good. Not zero. Okay, or alternatively, the rank of M is of course 2. All right. So then if you want to look at the similarity, so look at the left-hand side here, A times M, let's see this, A times M gives you something, and M times this guy is A tilde. This is M times A tilde, okay? Gives you the same thing. Now, the important thing is that you can represent A like this. You can represent A is M times a diagonal matrix with eigenvalues times the inverse of M. This is the diagonalization of A. Now, this should already look somewhat kind of like something you've seen before. This is a matrix factorization. Okay, this is maybe the third only? Yeah, I guess it's the third you're seeing in this course. So you've had the PA equals LU factorization. You've had the A equals QR factorization. And now you have a factorization where you took a matrix A and you represented it by M, something diagonal, inverse of M. Now, every factorization is good for something. Okay, and let's see what this one is good for. This is now the most fun bit ever of eigenvalues, what we're going to do now. So why is it good to look at diagonalization? Okay, this is diagonalization factorization. This is one way you can call this. So let's take powers of our matrix. Okay, so what we've seen is we've seen that A was M times lambda. Lambda is what I called in general in a similarity transformation. That was like the A tilde. The reason this I'm calling it, it's distinguishing between lambda and A tilde, because you know A tilde, sometimes that lambda is not going to be exactly this. I mean, lambda here is a very nice matrix. It's, you know, lambda 1, lambda 2, up to lambda n. It's just a diagonal matrix. In other cases, you won't have this exact lambda. Maybe you'll have something that has like blocks in it. And that's something you call the Jordan decomposition. We won't study this fully. Or maybe you do a completely different similarity transformation. But this is kind of the most common one. And that's, you can do that when the matrix is diagonalizable. And that's when M has the eigenvectors here. And the eigenvectors are non-singular. Or sorry, the matrix of eigenvectors is non-singular. Okay, so that's that times M inverse. Now, some of you might be wanting to put a transpose here. Just hold your horses, just wait a few minutes. You could do that for sure when the matrix is symmetric, okay? So that's gonna come to symmetric matrices, such as in data science, the covariance matrix, which is a symmetric matrix. But for now, we just have this. So we have A being this. Now let's say we want to look at A squared. Okay, so A squared is M lambda M inverse M lambda M inverse. What could be more fun? I mean, this is really as good as it is. You just cancel these guys. So then you get M lambda squared M inverse. What's the matrix lambda squared? Is it easy to compute or hard to compute? Computationally or symbolically or some combination? You know, generally when you do some things, it's easy, right? Because diagonal. So lambda squared is simply, you know, m times the scalar. I have a problem with my matrices. I put this one here very angled. Should make this lambda 1 squared, lambda 2 squared, up to lambda n squared. So you can even do it symbolically if you're looking for formulas, or you can computationally do it easily. And of course, you can continue this, this joy, and you could say that a to any power, take n, let's not use n because that's often the size of the dimensional measure. Let's say k is just going to be m times lambda to the power k times m inverse. So we'll go out in a minute. So this is what diagonalization is good for, and we'll see an example just after the break. And just keep in mind, if this lambda was not like a diagonal matrix, this would still work, but then the joy of taking a diagonal lambda to the kth power is not as useful, but still it's sometimes useful. Okay, so this factorization, the diagonalization factorization, is very good when you're thinking about matrix powers, and we'll spend the time after the break speaking about that. Any last question? All right, so we'll start in the hour. That's in 9 minutes. Enjoy the break, and I'll come a few minutes before. All right, I'm back. If there are any questions. So there's a question, when is a squared do? What do you mean by do? A2, I guess you meant a squared. Can you just explain the question a bit more? Oh, when is a squared due? I mean, like, when is a2 due? Okay, so you mean assignment 2, okay. It's not a squared. We can call it assignment squared, due. So it's due in October 15th. Yeah, that's when it's due. So first question deals with least squares. Second question deals with companion matrix. So it's actually interesting. So this companion matrix has eigenvalues which are written in the matrix. So it's a very structured matrix, and it, oh, you can't see it. Sorry. Let me actually share the. Let me share the assignment. Okay. You can now see it, I assume. So the first question deals with least squares, and I would get to it ASAP, just to kind of get things out of the way. The second question, after this lecture, you have all the knowledge for the second question. It deals with the companion matrix. So the thing is, look, let me give you a bit of philosophy here. So, you know, when you're solving for eigenvectors, eigenvalues, or eigenvectors, but when you're looking for the spectrum of the matrix, you're looking for the eigenvalues, you're not solving a general polynomial. You're given a matrix. But it turns out that you can have this companion matrix which exactly encodes the polynomial in it right there. So then you can compute its eigenvalues right there. Okay, so that's a companion matrix. And so you have enough knowledge for this one. And what we're going to do now, just after the break, in about 30 seconds, is deal with the dynamical system, and this is like this one. So this one deals with owls and mice, and the owls and mice reproduce in a coupled manner. You know, mice are born, owls have a lot to eat. Owls, there's a lot of owls, they kill some of the mice. You know, so it's a dynamical system, the relations between the two. It's of course a toy example, but that deals with that. And the next one we still won't get to today, but for some aspects we will get to. So that's a symmetric matrix, and that's quadratic forms. And here you need to take a selfie. You don't have to use a selfie. If you prefer a picture of your dog or somebody else, or just somebody else's picture, something else, do that. And you're going to do some compression. So that's your assignment. Okay. All right. So what we saw, I'm continuing. So what we saw is that powers of the matrix A, by the beautiful fact that M inverse cancels M and M inverse cancels M and M inverse cancels A, are just the powers of the similar, matrix A tilde squashed to the left and to the right with A inverse. Okay, in that similar matrix, again, if you do diagonalization, the similar matrix will be this beautiful guy. Okay, so just if we want to see it, let's take our matrix A to the power 20. The reason I did this float here, if you do A to the power 20, A is just a matrix of integers, you just get these very big numbers. Okay, so this casts it, you know, or cast or change type to float 64. Okay, so that's a matrix A. That's our A here is just the boring 1, 2, 3, 4 matrix. Okay, so instead, what we can do is we can do M times the diagonal of, and I'm here taking the eigenvalues of A, and I'm putting each one by itself to the power 20. Okay, notice the dot raise each eigenval to power 20. So there's no matrix multiplication in this diagonal. Okay, times the inverse of n, and you get the same thing. So let's see in principle how this thing can be used. And it's very related to dynamical systems. And there is a chapter in VMLS. So let me just suggest, I mean, you guys are busy now, but if you go to the VMLS book, we didn't cover anything explicitly really from this chapter, but there's a very nice kind of chapter you can just quickly kind of just flip pages through and have a read. And it's more of a modeling chapter, and it's a chapter here that deals with dynamical systems. Now, this book, VMLS, doesn't actually have spectral properties of matrices. It doesn't have eigenvalues, eigenvectors, singular value decompositions, and things like that. So in a sense, it's more elementary. Nevertheless, if you go to chapter 9, it's just a quick little read of what is a dynamical system. Okay, so dynamical system is basically you've got the state, and you've got some matrix that operates on, that's a linear dynamical system that operates on the state, and the state keeps evolving. Okay, so you can see a lot of examples, etc. Okay, population dynamics, yada, yada, yada. All right, but we don't have time to really get into the modeling aspect of linear dynamical systems. But now what we're doing is using this is actually very important. Okay, so let's see how. So let's do an example with a very silly dynamical system, which is the Fibonacci numbers. Okay, it's just an example that's nice to see because everybody pretty much knows about the Fibonacci numbers, but you now have the tools to, and I did this with class last year, I won't do it fully this year. You now have the tools to explicitly compute the formula for the nth Fibonacci numbers. So let's do phi. Does anybody know when he lived roughly and where? Fibonacci, wild guess. So 2,000 years ago, 3,000 years ago, 1,000 years ago, Fibonacci. Wild guess, where? 1,000, yeah. So around 1,000, and yeah, Italian. And I think Pisa, I'm not sure, so don't quote me on that, but Wikipedia can tell us. But what he did was actually, you see the fact we have 10 fingers and the base 10 numbers. So I believe he was responsible for bringing this decimal system that we use from the Arabs and Persians onto Europe. I think so, I'm not sure. But anyway, the Fibonacci sequence, we can do something like, for example, 1, next number is 2 because that's the sum of 1 plus 1. Next number is 3 because that's the sum of that. Next number is 5 because that's the sum of 2 and 3. Next number is 8. What's the next number? The Fibonacci sequence. 13, etc., etc. And let's do it like one more. 21 must be. Okay. Okay, come on, one more, 34. Okay, and one more, 55. Okay, and the thing goes on forever. So this is like a sequence where you've got, let's do it like that. So it's like yn is yn minus 1 plus yn minus 2. So this is a recursion. It's a second order linear recursion. And fine, okay, we can do that. But what we can also do is we can represent a vector. We can represent a vector xn, where the vector xn, I hope I'm doing this in a solid manner. The first coordinate here is going to be yn, and here it's going to be like yn minus 1. So this is like current, and that's previous. You see, if you want to know at any time, I'm like getting now, let's say this 34 depends on the previous, which is maybe the current, and the one before that. So you can represent the state of the system as a two-dimensional vector. Okay. If you do that, then let's see if I'm doing this correctly. Then what you can do is you can do 1, 1, maybe 1, 0, something like that, maybe, times xn minus 1. And you can say that this is the Fibonacci recursion. Let's see, let's just write it out. So I'll write it out just a bit more. So I'll write, you've got here the yn equals 1, 1 times yn minus 1, yn minus 2. That makes sense. And yn minus 1 is 1 times yn. Yeah. So the sum of these two via here goes into this. And then this, you all the time kind of the one that's current, then it becomes the previous. So am I correct? Yn, yeah, yn minus 1. This multiplies by this, and that's like the next one. Keep in mind, this is like, I maybe wrote this in a confused manner. This is like xn, and this is xn minus 1. Okay, so the state of Fibonacci takes it from xn to xn minus 1, like a linear dynamical system. Xn is axn. You see, the matrix kind of simplifies, or in this case, might appear to complicate, but actually, we'll see how eigenvalues can be used here in a second. All right. So, and let's start at x1 being like 1, 1, or we can even say 1, 0, if we'd like. Okay, depends how we want to start. Okay. So what you do is say, what's x2? x2 is ax1. And what's x3? x3 is a times x2, which is a times x1. Or you could just write it as a squared x1. And similarly, if you continue, when you get to like xn, you just get a to the power, in this case, n minus 1 times x1. Okay, so what you need to do is you need to take matrix powers if you want the nth element of Fibonacci. Now keep in mind, every child in school knows how to calculate the Fibonacci, but if somebody asks you what's the thousandth Fibonacci number or the hundredth one, then how do you get that without actually doing the recursion? Well, using this kind of decomposition, we can actually get a formula for it. We won't do it all the way. I'll just actually show you the final formula. Okay, but you can do it in principle. And it's just 2 by 2 matrices. This would be like an alternative homework assignment. Okay, you can do it for practice if you like. If you want to derive the formula, not a bad exercise. So what's the idea? What's the idea? Let's take our matrix A, which is the core of this linear dynamical system. And in the homework, you have a different linear dynamical system that's kind of slightly more interesting than Fibonacci, but also 2 by 2. And in general, sometimes people deal with linear dynamical systems here where the matrix A is like a dimension 1,000 or 20,000. Okay, so with many, many variables. So if you're doing short-term weather simulations, that's a dynamical system. Okay, you'll often linearize a nonlinear system around something linear, and then you could get a linearization of that, stuff like that. Okay, so our plan is to write the matrix A as M, lambda, M inverse. Okay, that's the plan. So what do you put in lambda? And lambda is just lambda 1, lambda 2, the two eigenvalues of Fibonacci. Now, you can do this analytically, and I actually suggest it's a good exercise to do at home, and then you could see that the eigenvalues are, you'd get them as a golden ratio and the inverse of the golden ratio. Okay. But I just want to move on to other things, so I won't spend a lot of time on that. So the matrix A here, I'll just break this into 2 bits. So here's a matrix A, and this actually happens to be the golden ratio, and this, like, I think inverse of golden ratio, or 1 minus the golden ratio, 1 minus the golden ratio. Not sure, but related to the golden ratio. Okay, so you can get these symbolically. Okay, but look up wiki for relation to golden ratio, because the characteristic polynomial looks like a very this is not critical for the course. Looks like it's kind of a very common second order equation, second order polynomial, and these are the eigenvalues. But first, let's just compute Fibonacci manually. So we start with a state x, say 1, 0, and we say the nth Fibonacci number would be the x1. x1 is first coordinate of vector x. Okay. And we continue iterating this way, so we get a 1, 1, 2, blah, 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 up to like the 10th is 55, etc. Okay, so we've iterated it. I mean, there's nothing special about that. Now, let's do it by actually being able to compute the nth Fibonacci number directly. Okay, so how do we do that? Let's define lambda, in this case it's called capital lambda, as a diagonal matrix of the eigenvalues of A. Okay, so this is our lambda. And let's call M the eigenvectors of A, Mi the inverse of the eigenvectors of A. Okay? And yes, the matrix here is diagonalizable. So the eigenvectors span all of Rn. Okay. Okay. And then here is our, our formula for Fibonacci. What we do is we do M times lambda raised to the n minus 1 times Mi, just like we wrote on the iPad before. And we take the first coordinate. Okay, so this computes the n minus 1 matrix power of A times initial condition, which happens to just be 1, 0. Okay, so I mean, we can multiply all this times 1, 0, and then take the first coordinate of that. Okay. So then, if we run Fibonacci, we get the same thing. Here you get some numerical error, very minor, because you're actually, you've got this M and this M inverse. But what I suggest doing is, if you actually do Wikipedia Fibonacci Wikipedia, so using the Fibonacci numbers, let's probably be here. So using the general formula. So come on, so many stories about the Fibonacci numbers. What we want is just a general formula. So here is a formula for the nth Fibonacci number. Okay, I mean, this is not something a grade school student knows just like that. How do you get the formula for the nth Fibonacci number? the standard way to do it is doing exactly what we did here, only doing this analytically, only doing this thing analytically. So M is a 2x2 matrix. You have it all analytically. You can write its inverse and you do all the multiplications. And lambda, you have the eigenvalues analytically. You take the n minus first power. You do a bit of algebra. I did this in class last year and students did it as well. And you get the formula for the nth Fibonacci number. So it's a bit of work, but I suggest working with it. Here, this is a golden ratio with psi. Okay, that's 1 plus root 5 over 2. Okay. So that's like an example of working with a dynamical system. Questions about that? Okay, now the next example for dynamical systems, which I really like, is Markov Chains. That's from Statistics with Julia, but we might get to that just a bit later because I just want to make sure that we do cover symmetric matrices all the way. Okay, so that's another example. It has to do with this thing called Markov Chains. I assume some of you have heard of Markov Chains. So Markov Chains are probabilistic models of random processes where the next state is distributed according to a distribution based on the current state. I hope we'll get time to get this to the end of the day, but I'll move that. And if not, I'll push it on when we meet next. Now, here's another example, and this is a shear matrix. Okay, this is a non-diagonalizable example. So this is non-diagonalizable is a case where this kind of decomposition, the similarity transformation between the matrix A and the diagonal matrix of its eigenvalues does not work. Okay, so one sign for this that we might be in trouble is you see the same eigenvalues, But that's not always a sign. So I mean, what I want to say is if we have distinct eigenvalues, then it's always diagonalizable. But there are cases where you have same eigenvalues and it's still going to be diagonalizable. For example, what are the eigenvalues of the identity matrix? What are the eigenvalues of the identity matrix? 1. So there's only a single eigenvalue of the identity matrix. But what are eigenvectors? Can somebody give me a vector that's not an eigenvector of the identity matrix? So the identity matrix in Rn. Unit vectors are example vectors, but actually anything. All vectors, right? All vectors. So unit vectors are like the canonical eigenvectors, but any vector, identity times any vector, and we're not allowed to speak about zero vectors, right? Is 1 times that vector. So all vectors are eigenvectors of the identity. Okay. So what I want to say is, and the eigenvalues are all the same. But in this matrix, the eigenvalues are the same, and it might be trouble. And if you look at the eigenvecs, then what you get is you actually get the same eigenvector on both sides. So this matrix here, you see you get a 1, 0 and negative 1, 0, but negative 1 and 1, you know, when you call eigenvecs, you can get a negative that or a positive 1. You don't really have control of what's happening. So the effective rank of this matrix is rank 1. It's effectively singular. Okay. So the null space of this matrix that we called B earlier in the lecture is one-dimensional when the eigenvalue is repeated. So this specific matrix here is non-diagonalizable. So that's like the standard basic small example of non-diagonalizable matrix. But I just want to say don't really worry about it. So this is not something that's going to appear on the quiz, and it's also not something that's extremely common, although in some fields of math it happens a lot. I mean, shear matrix is common and sometimes it appears. Anyway, that's not the key issue. Okay. And we are now coming to the next part, which is these beautiful matrices that are called symmetric matrices. Okay, I mean, you know about symmetric matrices for a while, but we'll now exploit the two main properties of symmetric matrices to do a whole lot. And this is now getting a bit closer to data science. Okay. Although I would argue that dynamical systems are also related to data science, because anything that has to do with kind of a linear model evolving, sometimes a data scientist needs to model such things and deal with models. Okay, so new subsection, symmetric matrices. Okay. So what I'm doing here is I'm taking a 5 by 5 symmetric matrix, random, and sorry, not symmetric, you know, not symmetric, most probably. Well, it isn't, okay? You know, because I mean, I know I control the seed, but of course, if you choose a random matrix, it's not going to be symmetric. And look, we've got some complex eigenvalues, okay? We've got a complex conjugate pair and 3 real ones. By the way, people sometimes plot the eigenvalues on the plane, just so you see this. It's kind of important. Real. Okay, let's let this guy warm up a bit and you'll see it. So it's important to plot the eigenvalues on the plane sometimes. I'll explain why. But that's kind of a side story. So the eigenvalues, give us a plot, please. Okay, now I think this is real. Sorry. Real. Okay. So why is this not? Maybe it's not the, so I want to take the real and imaginary part of the sorry, I should just stop. Real of, oh, I see. I'm sorry about this. This might not hurt. This might not be so destructive for you. So I'll do this for a sec. So I just want to get from numbers from a complex number its real and imaginary part. In the statistics with Julia book, there's actually an example for that. I remember this. So it's also in the index. So let me pull out this example. It'll take a sec. Not this, but this. Okay, so, oh, real and image. Okay, so real and image. Okay, you can do Julia, real and image. I think this will work. All right, cool. All right, so this is the plot of the spectrum. Okay, this is a plot of a spectrum. Now, it's often important to plot the spectrum. Let's just put the unit circle equals, look what I'm going to do. I'm going to do cosine of t okay, just do this. So so plot of cosine of applied to 0, 0.1 to 2 pi and sine applied to that. And I want you to see this because this is a plot that people often put. Okay, and let's just put aspect ratio 1. Okay, so this is what you'd call the plot of the spectrum of the matrix. Okay, now what you see here are the 3 that 4 of the eigenvalues, 2 of them are complex conjugates, and you've got 3 reals, okay? Just to make this kind of, you can do then a 50 by 50, for example. Okay, and here's a plot of the spectrum. And look, it's actually statistically, you see a lot of the spectrum is located around here, and this is your most severe eigenvalue. Now, what do I mean most severe? Well, we actually didn't get to speak about this. I'm moving back for a second when we spoke about dynamical systems, but let's get back to dynamical systems just for a sec. So you see in a dynamical system, we had the a to the power k was our matrix A tilde, which was lambda, diagonal of lambdas to the power k. So think now of this diagonal of lambdas. If all those lambdas were smaller in absolute value than 1, they might be complex, but let them be in smaller in absolute value than 1. What happens to a number smaller in absolute value than 1 that you take to a power k? It goes to 0. As opposed to that, if you have a single lambda that's greater in absolute value than 1, then it's actually going to blow up and go to infinity. And when you analyze dynamical systems, you sometimes call these things the modes of the system. So in very loose language, the modes is the eigenvalues in a sense. So there's a comment, I remember something in control systems, but where the system stabilizes, you can use the eigenvectors. Is that related? No, you can use the eigenvalues. Yes, for sure. So a stable matrix is a matrix with all eigenvalues in the unit circle. So this matrix that we got here randomly is not stable. Okay. So it's a matrix where when you apply the linear dynamical system and again and again and again, everything will go to 0. Fibonacci numbers were also not stable. I mean, Fibonacci grows. Okay, so this picture tells you a lot. I should also say that if you're looking at a continuous time system, and we might get to speak about that, or it might be part of your project, then what you have is a linear differential equation. You don't have a different system, but it's a continuous time dynamical system. And then you want your eigenvalues to be on the left-hand plane. It will make sense if we speak about it, if we get time to speak about it, but it's not critical for this course. Okay, so back to reality after we took this kind of diversion, but I actually wanted you to see I battled here with finding how to get the real part and the imaginary part, and here is just plotting unit circle. This is a plot of the eigenvalues. Good, it's a scatter plot of the eigenvalues. Okay, now, nothing special. Let's go here. Let's do random again, set the seed again. Take A temp to be a random 5 by 5 matrix and take A to be A temp plus A temp transpose over 2. This thing is called symmetrizing a matrix. Well, that's what's called kind of loosely, symmetrizing matrix. The matrix A is now a symmetric matrix. Okay. Eigenvalues, they're real. Okay. And for any symmetric matrix, it will be real. Of course, you have non-symmetric matrices that have real eigenvalues, but this is the property that's going to be very important. Okay. So, and just if we might as well see it if we're doing this for a sec. Now we're able to plot eigenvalues. Let's call this EV. You see, the eigenvalues of symmetric matrices just sit on the real line. Okay. In this case, some were negative, and it'll turn out that if they're positive, then we'll call those matrices positive definite matrices. Okay. So within the class of symmetric matrices, matrices that have eigenvalues just on the positive side are called positive definite, or if they can be 0, is called positive semi-definite. Okay, 0, by the way, means that the matrix is singular. This one is close to singular here, but it's not. Okay, and this matrix is not stable. Okay, all right. Now let's look at the eigenvectors of the symmetric matrix M. Okay, you can see a whole lot from this eigenvector. So again, I want to correct myself. It's not let's look at the eigenvectors. Let's look at eigenvectors returned from the eigenvex function, where we know that the first row, the first column maps to the first one, and the second to the first eigenvalue, and the second one to the second one, etc. I mean, of course, there are many different representations of the eigenvectors because we could stretch it. But let me do this, m times m transposed. What did we get with m times m transposed? Identity, right. So what does it mean? What's a matrix M? If a matrix times its transposed is an identity, what's a matrix M? What adjective does this matrix get? It's a consequence, it's invertible, it's orthogonal. That's the one, right. So it's an orthogonal matrix. Orthogonal matrices are invertible with the inverse being the transpose. This is, you know, at this point, after we see this, and we say, hey, let's call M Q. We typically call such matrices Q. We didn't know that, okay? So look, the M transposed is just like the inverse of M, okay? Here I'm just checking that the M transposed is like the inverse of M. I mean, you see here, but this shows us, you know, shows you that M transposed is inverse of M. So M transposed is the right inverse of M, and since M is square, then it's also an inverse. Okay, so it's also a left inverse and an inverse. This, by the way, here is something called a matrix norm. So in Julia, we applied here norm on it. You see, I'm applying norm on this matrix, which is a difference of two matrices, and I just want to kind of make sure that this is really all zeros. Okay, so that's what it is. We didn't get to matrix norms yet, but we will. Okay. So here's a claim. I mean, you just saw this. We saw this on a random matrix. Seeing something on a random matrix is not, you know, is not the best thing to do. But it's also true if I choose a different random matrix, I'll change the seed and I'll get a different random matrix. Okay, so here this one has a different spectrum. See, the spectrum is different, but it's all also all real, and m times m transpose. But the math tells us that the eigenvectors are orthogonal. Now again, I want to say we can choose the eigenvectors as an orthogonal set. Okay, and here is a claim, and we'll just prove this the next time we meet, because we're going to focus on other stuff. We've just had so many proofs today, and this is like an important one. Okay, so for symmetric matrices, eigenvalues are real. Enough with this complex eigenvalue stuff. Okay, and there exists an orthonormal set of eigenvectors. Okay, so this is nice. So if there exists an orthonormal set of eigenvectors, can you have two vectors that are, or let's say a set of vectors, can you get a set of vectors that are orthogonal, but are not independent? Can you get a set of vectors that is orthogonal but not independent? No. You cannot. No, no, no. And we proved it. We wrote this in this, and you multiply it from the left. There was actually a proof of that in one of the lectures. Okay. So since they're orthonormal, they're independent. So if they're independent, what does it mean? It means that the matrix is also diagonalizable. So this similarity transformation here, this M, exists. You have one. You have. And it even means more. It means that instead of M inverse, what can we put here instead of M inverse? You can put M transposed. So diagonalization of symmetric matrices, real joy, just fun. Because you don't need to do inverse. Okay. Let's see this. So symmetric matrices are always diagonalizable, and a symmetric matrix. So symmetric matrices is common to represent by S, not necessarily, but it's common. So S is here a symmetric matrix. You can write, instead of the M, you'll write a Q, and this was the A tilde of the lambda, and that's Q transposed. Now this is big. This is called the spectral decomposition for symmetric matrices, and this is getting into some useful domain, useful territory. And it's useful for data compression, and it's useful for what's called PCA, and other things. So let's explore this just a bit more and see an example. Okay, and we'll get to prove this kind of very natural property of symmetric matrices. We'll do this when we meet in 3 weeks, actually. Okay. I mean, you can please come to the consultation hour as well. So I've had very little attendance in the consultation hour. Once I was asked a question in the consultation hour, I wasn't really able to answer. I'm sorry about that. But typically, I can, and just come to the consultation hour and I can help. Okay, so symmetric matrices. So we've got a symmetric matrix S, okay? And we know here that Q is, you know, the eigenvectors, okay? Chosen orthonormal. So any two eigenvectors will be orthogonal, but we're also choosing the orthonormal version, okay? We like the orthonormal version because then Q transpose equals Q inverse, okay? That's what. And then we've got here lambda. And then we got here Q inverse, but we're even lazy. We don't do an inverse, we just do transpose, okay? Now, if you actually compute this thing, you actually represent this product. So there's different ways to represent it, but work this out and see that this is nothing but, let me actually write Q, I'll write it like this. I'll write Q, I'll call this Q1, Q2, up to Qn, okay? These are the eigenvectors that are chosen orthonormal. So then what I can do is I can do lambda 1 times Q1, Q1 transposed. This is a matrix. What's the rank of this matrix that I've just encircled? What's the rank of this matrix? The rank of this guy. What's the rank of this yellow thing? 1. It's a rank 1 matrix. It's an outer product. Okay. Plus lambda 2 times Q2, Q2 transpose. Plus lambda 3, Q3, Q3 transpose. Plus lambda n, Qn, Qn transpose. So this thing, which you can just write as sum I 1 to n lambda I Qi Qi transposed, is called the spectral decomposition. Spectral decomposition of symmetric matrices. Matrix, let's say. Okay, it's sometimes also called the dyadic expansion, just a different name from dyadic. Okay, I don't dare to write it if it's with the I or a Y. Dyadic expansion. Okay, each one of those rank 1 matrices is called a dyad. And later on in the course, when we're going to get to singular value decomposition, it's of the same type. Guys, this is powerful, very powerful, because what you're doing is you're taking the matrix S and you're writing it as a sum of rank 1 matrices. Now, let's say that S is 1,000. Come on, let's say that it's 1,000,000 by 1,000,000. Okay, 10 to the 6 by 10 to the 6. So S in its own right has 10 to the 12 entries. That's a lot of entries, it's a lot of memory. That's some very dense picture. Okay, some very dense picture. That's S, okay? Well, let's not say picture because a picture is not going to be symmetric, okay? But it's going to be a covariance matrix or something symmetric. So when you get to pictures, it's going to be something else, okay? But because it's symmetric, okay? This S has to be symmetric for this to have this nice form. All right. So this has 10 to the 6, 10 to the 6. How much information is in this guy? How much information is in just this red guy? You know, this is 10 to the 12 entries in S, but just this first term here. How many entries? In terms of kind of information usage. I mean, sure, when you write this outer product, it's also 10 to the 6 by 10 to the 6, but it's just 10 to the 6, okay? So, you know, you've cut from 10 to the 12, which is a very big number, to 10 to the 6 numbers, Okay, you've got a rank 1 approximation. Now, what you can do is you order the eigenvalues such that this eigenvalue is the highest one. Okay, and this is the second highest one in in magnitude. Okay, and this is the third highest one in magnitude. Okay, up to the last one. And then imagine that these guys here towards the end. I mean, this, by the way, this sum there's like 10 to the 6 elements in the sum. It's a very big sum. Okay, but imagine that these guys in the end, the lambdas, the eigenvalues are so small. So you're basically scaling down these rank 1 matrices to a very small number. So then if you want to truncate, if you want to approximate, you just keep the first few. First 3, first 4, first 5, depending. Now there's a question, is that PCA? Yes, that is a principle that's happening in PCA, but we'll speak much more in PCA. So PCA, for those that don't know, principal component analysis, a data compression, data reduction mechanism in data science, where you take data where you have, say, n features, and you do a linear combination of the features, and you find maybe 3 or 4 or 5, maybe 7, maybe 20 principal components, which are linear combinations. That's in a sense what you're doing in PCA. So this is, if S is your covariance matrix, as I'll show now, that's what's PCA. But a different view of PCA is via SVD, which generalizes this thing. So SVD allows you to do this for non-symmetric matrices, these types of things. Okay, all right. So you see, those few eigenvalues here are going to be they will tell us that the meaning of the eigenvalues come in how much information is in this data, and we'll only choose the first few because we'll want to throw away the rest to compress or to summarize data. That's in a nutshell how this works. So let's just see an example, and that will be probably the end of the time we have to today. But and then I'll just summarize a bit, because I did cover. You did see a lot of things. It's not I covered as you took in a lot of things, or you listened to it. So thank you. All right. So what I'm going to do here is I'm actually going to generate synthetic data. Okay. So I'm using the distributions package, and this MV normal is this here is generate synthetic data of length 3 from multivariate normal distribution. Okay, so I'm going to generate 10,000 points, and each time I do an MV normal, that basically gives me a random vector with this mean and this covariance matrix. So it's kind of a bit backwards in this example. What I'm doing is I'm first just generating the data, so like there are many, many points. Okay, so this is what's happening here. It's probably taking time because it's loading the distributions function or something like that. And then I'm going to plot this data, and what you see is, each data point is just 3 coordinates. I don't have here axis labels, sorry, but it's just the first coordinate, the second coordinate, and the third coordinate. This is a scatter plot. So this is like one data point, okay? But I've synthetically made them correlated according to this thing called the covariance matrix. I believe most of you know what a covariance is. A covariance matrix summarizes the covariance between the ith component and the jth component. We'll actually speak more on covariance matrices. I mean, they're one of the central things that you're learning linear algebra for. Okay, as a data scientist. So here's a plot of this. Now I'm going to forget the fact, as I often do in the lectures, that I actually made up this data. I mean, I live in an imaginary world, lecture, okay? And then what I'm going to do is compute the sample covariance from the data. So, for data science, this is sometimes where the story starts. Okay, so I've got this data which is like these things, and I compute the sample covariance. So this is what the cov function does. the cov function gets kind of an array of arrays of data points, and it does a covariance matrix. So basically what it does is it estimates, oh, this was the variance. Covariance matrix, this is the variance of the first component, variance of the second, variance of the third, and this is a covariance between the first component and the second component, or the first feature, second feature, if you'd like. And what do you see? The covariance matrix, which I call here sigma hat, you do in sigma by just capital sigma plus tab. Okay. Sigma is often the notation used for a covariance matrix. In this case, it's the sample covariance matrix, is symmetric. Okay, and that's kind of by design, that's how it is. So then, what I'm going to do is I'm going to look at the eigenvalues of this covariance matrix. Okay. Now, the covariance matrix is by the way always positive, because positive definite. So I haven't spoken about this yet. This is the content of the next lecture that will continue in 3 weeks. But the eigenvalues are going to be positive definite for the covariance matrix, because the covariance matrix has a property of being positive definite. Not all symmetric matrices are positive definite. Okay, so remember we generate some random symmetric matrix. You see it had negative eigenvalues. Okay, so just in the world of matrices, you go from non-square matrices, you can't even speak about eigenvalues. Square matrices, fine, you can have eigenvalues, real, complex. Symmetric inside, they have to be real. In there, you have something called positive definite, and covariance matrix satisfies this property. Okay, we'll see why later. So now we're computing the Q, which is the M matrix. You know, before was M. Before was M. Now it's Q. Okay, and let's keep in mind, Q times Q transpose is going to give us identity, right? This is identity matrix. Okay. Now, all I'm going to do now is I'm just going to order the eigenvalues according to their order. So I'm going to see that this eigenvalue is the most important. So this one is 2.3. You know, it's this eigenvector, this third one. So if I expand this eigenvector outer product with itself to get a rank 1 matrix times 2.3, that will be my rank 1 approximation of this covariance matrix. So what I'm going to do is I'm going to do the sort PEM. This gives me order of eigenvalues by magnitude. So, you know, I basically want with the flag reverse true, so I know that the third one is the highest value, the second one is second highest value, and the first index is the lowest value. Okay, because when Julia returns eigenvalues, it actually sorts it in the reverse manner. I could have just reversed, but it's better kind of to really kind of sort them according to the order. So then what I'm doing is I'm reshuffling the eigenvalues. So according to this permutation, this is reshuffle eigenvalues and reshuffle eigenvectors, both according to permutation. So you see, I've just changed because, you know, the order is something kind of arbitrary, but I want the first to be the largest. So now look, this is going to be my rank 1 approximation. I'm doing this very manually. Rank 1 approximation, you've got a minute. This is a rank 1 approximation. So it's the first eigenvalue times the dyad of the first eigenvector multiplied by itself, this outer product. So you get this outer product matrix. You know, if I do the rank of approx 1, it's not the, I didn't know this yet. It's not the, it's a rank 1 matrix. It's not the covariance matrix, but, you know, it's not sigma hat. And indeed, if I look at the difference between this first approximation, sigma hat, this difference is not 0. But look, sigma hat is not so different. So you see, this is 0.95, this is 0.98, this is 0.86, this is 0.88, this is 0.98. Ah, this one's quite off. Okay, but that's a rank 1 approximation. So I might say, well, that's not enough for me. So then what I'm going to do is I'm going to take a rank 2 approximation. So this is the first rank plus the second element of the sum. We could have automated this. We could have written this in a much more efficient way, obviously. Okay. And if you look at this, this is a rank 2 approximation. If you look now at the norm difference, and this is matrix norm again, which you don't know exactly what matrix norm it's using, etc., but you know that if what you'd put here would be 0, you'd get a 0. And you know that as the two things get closer and closer, the matrix norm goes to 0. Okay, so you're like a user of matrix norm. Look, rank 2 approximation gives you a very close matrix norm. Okay, and indeed, if you compare approx 2 to the actual sigma hat, look, this is already 0.97, 0.97, 0.37, 0.38. So you might look at this and then you make kind of a subjective decision. You say, ah, okay, I'm happy with a second rank approximation. Of course, if you go to the third rank approximation, it's no longer an approximation. So now I'm adding the third element of the expansion. It's an exact. So, you know, this is an exact match. So there was then no real reason for compression reasons to do that. So this idea here is the basis for what's happening in principal component analysis, and it might show you the strength of this decomposition. So out of time, but maybe you have a question or two. No? No questions? It's been too much. Okay. So I think I'll summarize with that. Very quickly, what we did today, we reviewed the least squares, pseudo-inverse, and projection matrix, and then we started this new unit on spectral properties and quadratic forms. And we saw a whole bunch of properties of eigenvalues and eigenvectors. And now we specialized to symmetric matrices. We still haven't proved that the eigenvalues are real and there's an orthonormal set of eigenvectors, but a very good use of that is this spectral decomposition, which allows you to approximate matrices by truncating the sum and not taking all of the summons. But if you take all of the summons, this thing is exact. And the other thing we did was dealing with dynamical systems, and that's by things like, this is the dynamical system step. Evolution. That's a lot. So thanks for hanging in there, and drop me a line on Piazza or in other means if you need anything, and see you hopefully on Friday in my consultation hour if needed. And there'll be one next week. Okay, bye-bye. Okay, somebody's saying we're getting to the good stuff. All right.